given a target amount and coin denominations. You may use each denomination as many times as needed, but order does not create a new answer. For amount 5 with coins 1, 2, and 5, we count every unique combination that sums to 5. One combination is just coin 5. Another is 2 plus 2 plus 1. Another is 2 plus 1 plus 1 plus 1. And the last is 5 1 coins. There are 4 valid combinations, so the output is 4. Example 2, amount 3 with only coin 2. 1 2 is short and 2 2s pass the target, so there is no valid combination. The output is 0. You are given an amount and an array of coin denominations. You want to find the total number of unique combinations that add up to that amount. Your immediate instinct might be to build combinations by checking every single coin for every single amount. But look at what happens. You end up counting 1 plus 2 plus 2, 2 plus 1 plus 2, and 2 plus 2 plus 1 as 3 separate answers. In combinations, order does not matter. We need a system that completely locks out these duplicate ghosts. Here is our massive paradigm shift. To completely eliminate duplicates, we process coins one denomination at a time. We invite coin 1 into our system and let it visit every single amount. Once it is completely done, we kick it out of the building and bring in coin 2. Because coin 1 can never sneak back into the room after coin 2 has entered, it is physically impossible to generate an out-of-order sequence like 2 then 1. We enforce absolute chronological discipline. Let's look at the underlying mathematical relationship. If you are standing at the 5-cent mark, and you decide to use a brand new 2-cent coin, how many new combinations do you inherit? It is equal to however many valid combinations you already found for 3 cents. By looking backwards exactly the value of your coin, you instantly pull those precalculated combinations forward, paying no extra loops to discover them. This maps beautifully into a single one-dimensional array where each index represents a mini target amount. We initialize our base case, dp0 equals 1, because there is exactly one way to make 0 cents, by choosing nothing at all. For any higher amount, its new total is simply its current value plus the value of its backward remainder. It is pure, clean addition, with no complex minimization or matrix storage required. This brings us to the ultimate code payoff. By putting the coin loop on the outside and the amount loop on the inside, we ensure our coins are processed strictly one by one across the entire array. The data naturally layers itself without duplicates, completing a linear sweep that solves a tricky combination puzzle with maximum speed and zero wasted memory. Let's write out the clean, space-optimized solution. We allocate a one-dimensional array called dp with a size of amount plus 1. Each slot represents a mini-target from 0 to 5 cents. We immediately seed our base case, dp0 equals 1. This represents the mathematical truth that there is exactly one valid way to make 0 cents, by choosing absolutely nothing. Every other slot starts at 0, waiting to accumulate its combinations. Now we activate our loops. With our coin loop on the outside, we isolate coin 1 completely. Our inner loop starts at index 1 and marches all the way to 5. At each step, it looks back exactly one slot, the value of our current coin, grabs the combinations found there, and adds them to itself. Because we are using only 1-cent coins, there is exactly one way to make every single amount. This sets our clean baseline layer. Next, the outer loop advances to coin 2. Notice that our inner loop intelligently jumps its starting position directly to index 2, since a 2-cent coin is useless for smaller amounts. At index 2, we look back 2 steps to dp0, inheriting that one way, updating our total to 2 ways. We march forward. By the time we hit index 5, we look back 2 slots to index 3, which already holds 2 ways, and add them to our existing baseline, bringing index 5 to a total of 3 unique combinations. Finally, the outer loop processes our last denomination, coin 5. The inner loop instantly targets index 5. It looks back exactly 5 slots all the way to our base case at DP0. It pulls that single combination forward, which represents using exactly one 5-cent piece, and adds it to our running total. 3 plus 1 becomes 4. With all coins cleanly processed, our loops naturally terminate. Because we processed our coins strictly one by one from the outside loop, we have completely locked out duplicate combinations. The final slot at DP amount holds our perfect, uncorrupted answer of 4 unique ways. We return the value, crushed in optimal linear time and microscopic space complexity. Let C be the number of coin denominations. Time is O of C times amount, because each coin performs one left-to-right sweep across the target amounts. Space is O of amount for the one-dimensional DP table, with no matrix and no recursion stack. The final pseudocode is short. Initialize the one-dimensional DP table, see DP0 as our base case, process coins on the outside, sweep amounts on the inside, and return DP amount.